但是我上课学的是信息系统，然后后面就后来怎么能在那7期，但是我后来就实习在北京实习了，大概在那个说你在百度，我在百度实习过，那个好几是百度在北京实习，我有点想说把两个创意公司，反正就因为我学2年的实习，我从12年11月开始实习，然后一直断过，为什么都是实习都不转正？我这本科在读的时候，他们都不会给我
Okay, let's get started. It's interesting that the crowd is a little lower today. I wonder if it has anything to do with that quiz. Before we start, I have a bunch of announcements. First question, people in the last row, am I audible? Yes. Okay. Second thing, again to the guys in the last row, can you read the smallest font on the slide? Okay, just to calibrate myself. Okay, announcements. We have a quiz on Canvas. It's quiz 0. It's supposed to test your prerequisites. I expect it to be at least reasonably easy for you. You shouldn't have to suffer. And it's due in a week. And someone asked me how this quiz and homework and they line up with the final grade. So all the quizzes and homeworks put together will be some 35 or 36% of the final grade. And I'm planning to have every quiz cost 1 point in the final. There's a survey online. It's not graded. It's mostly for my curiosity. You're welcome to answer any questions that you think are interesting, if you want to. I mean, there's no compulsion there. And there were some questions about registration. I've been handing out permission code. Is there anyone who is here but not registered and still waiting for? And are you planning to register, or are you just okay? Send me an email. I know there are people who just want to sit here, but you're welcome. Another one is you guys must probably try to get yourself accounts on the CADE machines. If you haven't done that already, most of the people who are in CS probably have already done it at least once. If you're new, you might want to just get yourself familiar with that. All our homework, the programming assignments have to run on CADE machines, and the first assignment will be available maybe in a week or something. You guys probably remember the dates. And we are still working out the details of TA offices and stuff. We'll keep you updated. Any questions about any of these things, logistics? Okay, good. So let's start our first real lecture of the semester, and this is going to be an introduction to supervised learning, just to kind of explore the space of supervised learning. What is supervised learning and why is it interesting? What are the various things we should keep in mind before we even start to think about our first learning algorithm? But before that, in the last lecture, we very broadly looked at the question of what is learning. And I attempted to give a few definitions of learning, none of which I am personally entirely happy about. But the main point I wanted to convey from the last lecture is learning is effectively the same as generalization. If your classifier, if your function that you've learned does not generalize on new examples, then you really haven't done any learning. And the other thing that we looked at was the badges game. Did anyone take a look at the full data on the website? Okay, either you're too shy or maybe you didn't take a look at the website. But in any case, today we'll be looking at a little bit more about the badges game. You'll probably worth looking at that data because we'll also have a few homeworks designed around that. Not the exact same data set, but tweaks of it and variants that are not as nice as the one on the website. We'll kind of add noise and make it more interesting. And we'll start formalizing the problem of supervised learning. So, to remind you about the badges game, this was this thing that someone did in a conference where every name had a badge and every badge had a plus or minus, and the attendees of the conference had to figure out what was the function that was used to create the plus and minus. And last week I presented 6 examples. Since it seems like you haven't seen the remaining about 194, this is your training set. So the question to you is not just what is the function that was used to create the plus and minus, but I want you to guess what's the label for a new name. Say Peyton and brother. What's the label for Peyton Manning?
Plus.
And what about Eli?
Minus.
Is that just because you think I have 2 examples and one will be plus and the other? So the real question is, how are these labels generated?
The second letter of the name is, if it is a vowel, it is a plus. If it is not a vowel, it is minus.
So you're saying if the second letter, so that's a good guess. In fact, that's a very good guess because I even have it on my slide. Okay, then that's not a guess at all. So that is an example of not learning. That's an example of not generalization. But in any case, so the second letter of the first name is a vowel, then you have a plus, otherwise it's a minus. But what I want you, and do you agree that it fits all these 6 examples? And if you actually go to the website and take a look at the data, you'll see that it fits all 200 examples. So let me just tell you that it fits 200 examples. So the question that I want you to think about is, one, how would you go about getting this function? If I just give you those 200 examples. Effectively the entire course is about trying different algorithms for determining that function without having any information, except the training set. The second question, which is actually more interesting, is, or on the slide it's the first question, how do you know that you're right? Just because this function fits 200 examples, how do you know you're right? And the correct answer there is not because I put it on a slide. So, is it enough if it fits 200 examples? Will it be always correct? Is this the magic function that was used by whoever created the data? And how do you even know that this function, given that the data set was just looking at names and a plus and minus, how do you know that the thing to look at are the characters? How do you know that, in fact, what are vowels? I mean, I don't know what vowels are. I mean, they are just ASCII code. You have A is some 90 something and so on. Vowels are, and consonants are an idea that we seem to all agree on. I don't know how, because you didn't go to the same high school as me, or whenever I learned about these things. So we have somehow incorporated background knowledge in designing this function. We are not searching over the space of every possible function, but we've somehow restricted ourselves to some reasonable functions. If I tell you the functions about name, you immediately start thinking about like the length or the kinds of characters and such things. So that's an important lesson in being able to identify, for any kind of a learning sort of setup. You need to be able to think about what background knowledge needs to be brought in to specify the classifiers. And the other question, of course, is did you use any learning algorithm? And I seem to have. Okay, by the way, I'm also conducting an experiment. This is the first time I'm using a Windows machine in 10 years. So things might not be as smooth as one might want. Okay, so let's talk about what is. So one, I'm not going to answer any of these questions at this point. My hope is at the end of the semester, if you come back to the slide and take a look at these questions, you might be able to answer most of them. And these questions keep coming up in pretty much every learning-based problem that you have to deal with. So let's move on to the topic for today, which is supervised learning. So what is supervised learning? Yes. And to introduce this idea, I'm going to basically spend the rest of today effectively defining a whole bunch of things. The first thing that's interesting in this space are instances and labels. There are two sets that are very interesting. There's something called the instance space. It's a set of all possible things that can be labeled. If you're labeling names, it's a set of all names. If you're labeling email as spam or not spam, it's a set of all emails or images or so on. Basically inputs to the program that's going to predict the labels. And the set of all of these things are called are called the instance space. And as a convention, I'll use the letter X to denote instances. Sometimes you'll also hear the word examples. And what we want to do is take these instances and assign labels to each one of them. And so that gives us our second set, the label space. The label space is a set of all labels. If you are building a spam detector, it could be spam or not spam. If you are building this name classifier, it could be plus or minus, true, false, it could be more complex objects. And what we are assuming is that there is this magic function, which I'll call the target function, and denote by f. And f is a hidden function that can take an instance from the instance space and assign a label to it. And what we want is to find this function. So this is a reasonable way of formalizing learning as the search for functions that agree with that have some properties. So learning is not search over you can think of learning as search over parameters, but more generally learning is search over programs or functions that take an example whose signature is X to Y. What makes this interesting is that we don't have access to this function. We are searching over this function, but we only have to find this function using certain side effects that this function has. In particular, the learning algorithm does not get to see anything about this function except its action. So what you have is you have a finite, possibly small number of instances of examples, and you get to see what this function f can do to those examples. That's all we get to see, or that's all the learning algorithm gets to see. And these sets of points are called the training points, or training set, or training data. And this training data goes into the learning algorithm, which is a black box or a blue box. And somehow this learning algorithm has to produce a model. I'll call the thing that the learning algorithm produces a model. The word model is thrown around a bit. It has a few different meanings, and hopefully from the context and just by hearing it multiple times, what it means will be clear. So the learning algorithm takes labeled examples and produces a function g. G has the same signature as f, except it doesn't have to be the same as f. So this protocol of learning, where you have labeled examples and the learning algorithm produces a function, is called supervised learning. Can you think of other ways of other mechanisms for learning? We spoke about some last lecture. What happens in that?
We don't have labels are given, but all the good labels are being provided by the program.
Or another way of saying the same thing is in unsupervised learning, you don't get to see the f of x. You only have the x. You basically do not get to see any manifestations of that function, and yet you are supposed to find that function, which seems like a bizarre expectation, and sometimes it works, which is kind of awesome. Okay, so what we have are the instance space and the label space, and using the training examples, we've learned a function g, and we are hoping that g approximates the function f. We are hoping that g mimics the oracle. How do we know that g is a good approximation? Yes. Let me repeat the answer. You use new examples to check. Seems like a reasonable thing. It's what we do in exams and stuff, if you think about it. And another way of saying the same thing is you draw a test example. Just randomly sample a test example from the instance space, and say we allow this Oracle function to label this test example. We also label this test example using our learn function G, and we check if it's correct or not. So in other words, we apply the model's prediction to test examples and compare to the target function's prediction. Just as even before I've defined training and such things, can you think of any reasons why you should not use test examples during training?
No.
Overfitting, but that's a word that I don't know what that means.
Basically, that it gets too specialized then, because the model will be specific to all the examples that you're training on, and then if you bring in new examples, because it was so specialized, it might make a lot of mistakes.
Okay, but there's a much simpler reason why you should not use test examples during training.
You might run out of test.
Well, someone here.
It's not a really valid test if
Exactly.
you're trained on it.
Exactly, it's not a valid test if you train on your test examples, because here's a learning algorithm that will do perfectly on the test set. You take the test examples, put it in a database. When the test example comes in, you look it up and say you produce the label. Have you done any learning? Yes.
I had a question, like, if we don't know the target function, how could we get a new example and put it through the target function?
Yes, that's a good point. We don't know the target function, but sometimes, even though we can't actually explicitly say what the target function is, we can execute it. And an example of that is, I give you a photograph and ask you whether there's a cat in it or not. It's easy for me as a person to say that, but I don't know what internal algorithm I use. So sometimes there are functions, we'll talk about that in a minute. But that's a good question, because if we know the target function, then there's no need to learn. So let me just summarize what we had. The general setting for supervised learning is we have training examples of the form x and f of x, or x and y, and f is an unknown function that we are trying to discover. And one little additional point to mention is, most of the time, that at least as far as this class is concerned, we'll look at the instances x in something called the feature space. And I'll talk about the feature space quite a bit now, but for now you can think of a feature space as there's a one-to-one mapping between every example, an email or a cat photograph, to a large vector that represents all the sufficient information needed for classification. Okay? And we'll look at examples of feature spaces in a bit. And for every training example, f of x is the label, and our the goal of learning, supervised learning in this case, is use the training set to somehow find a function that approximates f. And the label decides what kind of training problem we have. If the label is binary, then it's binary classification. If the label is one out of k labels, then it's called multi-class classification. If the label is a real number, it's called regression. And there are other such examples as well. Questions about just a big setup? I've told some of you before, I was told when I was an early grad student that the right amount of time to wait when I say questions is 30 seconds, because at that time someone will feel uncomfortable about the silence and ask a question.
I have.
Okay?
Why is linear? Why is regression? Are you referring to linear regression or
No,
something like that?
just regression. What was your real question there?
I was just wondering, why does regression always have to go to real? Why is that always what you're doing for real?
No, it's just the name that you give.
No, you're just. Okay,
Yeah, you could have more complex objects as well. You could have, for example, I might want to predict probabilities, or I might predict graphs, or I might predict functions, which makes it even more fancy. This is just like a few examples. And to answer the question that you asked earlier, what kinds of applications are best suited for machine learning? One of them could be, there's no human expert. I want to find some DNA binding sites, and really nobody knows what's going on. So we don't have the target function, and yes, question from...
Wouldn't binary classification be a set with 0, 1 rather than -1, 1?
You can always map, so let me ask the question again. Wouldn't binary classification, wouldn't the label space for binary classification be 0, 1 rather than -1, 1? And the answer is, it doesn't matter because you can always map it to, map one thing to the other.
It can basically anything, just separating two things.
Yes, it can be two things. And -1, 1 has some useful properties that we'll use later on. That makes the math a little bit nicer. But yes, 0, 1 also works. And in fact, as far as I'm concerned, I'm fairly certain I have some slides where I'll say 0, 1, some slides where I say -1, 1, because I really don't see the difference. So, yes?
Yeah, I understood this labels for binary classification, like whether it's a cat or not, and multi-label classification, like whether it is a cat, man, or
Yes.
a box like that. But what kind of labels do you give in this regression?
In what? In regression, it's a number. What's the stock price for Twitter tomorrow? Example.
If we like map like a multi-classification or binary classification to a number, right? Then are those then subsets of regression?
Hold on to that question, I'll come to that in a minute. Let me just get through this bit. So, sometimes we don't have access to the function because nobody knows the function. Sometimes we know how to apply the function, but we don't know what the function is. And that would be the case where of object detection or something about languages. And sometimes the function is just hard to obtain in closed form, and this is the kind of stuff that people in algorithmic trading like to play with, where I have to predict whether the stock price will go up or down. Was there a question? Yes?
So when we do supervised learning, it becomes very essential that the labels which are what we call as annotations are correct. So it may happen that two people are labeling
in fact, the most interesting cases are where there is noise in the data. There will be noise in the data. If you find data that does not have noise, then hold on to it because you won't find too much of that. And the learning algorithms have to be robust enough to deal with the noise. Some algorithms are, and some are.
But then it depends upon the amount of data we have, right?
Yeah, yeah.
If the noise is too much, then...
Yeah, yes. True. Okay, so some examples of binary classification. We saw this in the last lecture, so I'm not going to labor this point. Spam detection is an example of binary classification. Spam or not spam. You can think of, you can frame a recommendation system as a binary classification problem where will this person like that movie or not. You can frame malware detection, intrusion detection as binary classification. Sometimes you can kind of twist time series prediction also as binary because you can say whether you can ask whether some price will go up or down and things like that. So binary classification is has very broad applicability, and we'll spend a lot of time talking about binary classification. Okay, so the next thing I want to get to is what are the different questions we have to ask ourselves when we are trying to use supervised learning. And I'm going to rush through this slide because each of these points I'm going to spend a fair bit of time on. First we need to decide what's the instance space, because if we don't know what we are classifying, I don't know what we can do. And part of deciding the instance space is also figuring out what the features are. We need to decide on the label space because that's pretty much what defines our classification problem. But it might seem like an obvious question that the labels. If you have a problem, you know the instances and labels. But sometimes if you are actually coming up with a new application, you might actually have to spend some time deciding what are examples and what are labels. We need to, and this is a phrase that I'll throw around quite a bit. We need to decide something called the hypothesis space. The hypothesis space is a set of functions that the learning algorithm has to search over. Remember that I said learning is basically search of functions. So we need to specify what is the set of functions, and that's the hypothesis space. Having decided these three things, we need to decide what's the learning algorithm, and this last point, I'm not going to labor it too much, a large part of the semester, we need to decide something called the loss function, or to put it simply, we need to decide what is success. How do we know we are doing well, so that if we are able to formalize that in mathematically, we can define learning as just trying to minimize loss. So let's go over these points one by one. First, a couple of things about the instance space. Remember that, just to repeat what we saw, learning is trying to find a function that can take instances to labels and mimics this hidden target function. And identifying the correct instance space is very important. In particular, most of the time you can easily tell what an instance is at the level of is an email or a picture or a name or whatever. But what is really difficult is identifying the features, and this is where a lot of domain expertise comes in. And if there's one lesson I want to get through in this whole semester, it is there's no magic in machine learning. There's a lot of manual work so that we don't do future manual work. But upfront you need to decide things like what are features. And features, you can think of them as just, you have a bunch of sensors that are going to each example and taking readings. So you can have Boolean features. If I want to design a spam detector, you can have a feature that says, a Boolean feature that says, does this email contain the word free? True or false? If you could have real valued features that if you want to identify, for example, something about the name classifier, you might, if you feel that maybe the relevant thing to do here is the length of the name, then you might want to add that feature. What's the length of the name? Could be real value. Or if you want to build a stock price predictor, you might, one reasonable feature could be what was the value of the stock price yesterday. So, just as an example, just to get us thinking about features, let's brainstorm some features for this classifier that takes us from names to plus or minus. What was the one feature that gave us the answer directly? A lot of mumbling.
Being able to detect the character in the second space.
Yes. So you want to basically, if you can have a function, and this is deterministic, because given a name, you can write a function that's just, all of us know how to write that code. And there's no learning there, but identifying that is important. But say I change the target function. Say the target function has nothing to do with the second letter. It's something that only I know and nobody else. And you assume that I'm a reasonable person and I'm not just randomizing those labels. So if you had to train a new classifier, can you come up with some features?
Length.
Someone said length. Yes, length again.
Consonants, vowels.
What is that? What do you do with consonants?
Number of consonants.
Number of consonant. Good. So you're getting the idea. So basically, you have to upfront design, or this is one narrative in the machine learning story. Before you start the whole classification process, as a domain expert, as somebody who understands names very well or how names work, upfront you have to decide on what are the kinds of features or attributes that might make for a good classifier. And these features sometimes won't work. So what you do is, that's where the narrative breaks down a bit. You try some features, it doesn't work, you try more features, and so on. Yes?
And in the case of badges, is more features typically better? Just saturate it with just... I feel like if we saturate with just infinite amount of features, that might cause more harm than good.
That's very good intuition, and keep that thought for the next maybe 4 weeks. because we will prove mathematically that is correct.
You'll see, I'll remember it.
Yes. So just to make the point again in a different way, what we have to do is write down these functions called feature functions that take inputs to vectors called feature vectors. And these feature functions, you will also hear the name feature extractor thrown in. Feature extractors are deterministic for the most part. In fact, learning these functions themselves is a hot area of research. But we won't have to do it. Let's not worry about that for now. Let's pretend that these are deterministic functions. And these feature functions convert examples into lists of attributes. Or, if you're more comfortable with the mathematical version of the story, it converts examples into huge vectors in n-dimensional spaces. And identifying these feature vectors or feature functions is a crucial aspect. So these feature functions could produce real valued features or Boolean. And in general, for most of this class, I will represent these feature vectors as n-dimensional vectors. Very often I'll represent them as n-dimensional Boolean vectors, which are basically points that are at the corners of a big Boolean cube, or it could be points in n-dimensional space. At this point, I'm sure at least one of you is feeling a little worried about the idea of n-dimensional spaces. And if you aren't feeling worried, either you've seen it before or you're really not paying attention, because it's not clear what an n-dimensional space is, or at least you're hearing it for the first time. And the answer there is very easy. The mathematician's answer to how do you visualize an n-dimensional space is something that I say all the time. You visualize n-1 dimensional space and just apply induction. And we know how to visualize two-dimensional spaces, so the problem is solved. I don't know what the induction step there is, and so that's why you don't trust mathematicians too much. In any case, the point is, there's a one-to-one mapping between, or there's a deterministic mapping between examples and feature vectors, and each feature vector is a point in some large dimensional space. Just as an example, just to point out that there's nothing magic here, this is an example of a point in two-dimensional spaces. Okay? And how do you go from these functions that say second letter of the first name to a vector space? Here's an example. You basically encode all these discrete objects as vectors. So A becomes this vector here. A becomes this vector here, where there's a 1 in the first place and 0 everywhere else. B goes to a second one where there's a 1 in the second place and 0 everywhere else, and so on. And the length of this vector is obviously 26. Only one of these points is 1, everything else is 0. This is also called a one-hot encoding sometimes. Questions? And it's fairly obvious how you can take real valued features to a vector. Really, length of this is a vector of size 1. The length of the name is just a vector of size 1. And if I want two features, then you have, let's say I want both the second letter of the first name and the length, then you just stack them on. So you get 27 dimensional features instead of 26. And either this is blindingly obvious or this is very confusing. I've never seen anything in the middle. I don't know, from your faces I can't tell which one of these two it is. Yes?
Another question, if we know how we're going to label it, how we're going to apply a label, for instance if we were looking at vowels, then would we, instead of having 26 spaces for all the letters, could we just have a binary space?
Yes. Yeah.
So this would let us keep all this distinct letters, but if
sure, but you don't know, right? upfront you have no idea that what's the right attribute that decides the label.
So typically up front, you just pull like as many features as you can?
Exactly. You just throw in what you can and hope the learning algorithm picks up the ones that are good.
Feature vectors have to all be the same size, right?
Yeah, yeah. For the most part, there are hacks to deal with. You can basically make it the longest size.
Okay.
And pad them at 0 if you want.
Okay.
Yes.
Can a feature itself be learned by the learning algorithm?
Yes, it can, and we won't be talking about that very much, but that's the idea of a pipeline or a joint model. A pipeline is an example where the feature is itself output of an classifier that was learned on something else, and that classifier itself was learned on some other features, and so that's how pretty much all of many natural language processing applications are built, where you have this whole big pipeline of classifiers. Yes.
Why are you encoding this with, why are you using ASCII or some other way to encode this? It seems space inefficient.
That's an excellent question. The reason I don't want to use ASCII here to encode is because what's ASCII for A? Small a. I think it's 97 or something.
It doesn't matter though, it's just a number.
Yeah, sure. It's 97 and B is 98 and C is 99. So the distance between A and C is 2. The distance between A and B is 1. You are imposing an arbitrary ordering of these letters and an arbitrary notion of distance. So the game here is not to encode as compactly as possible, but to encode as informatively as possible. Okay, let's move on, and if this is not clear, this will become more clear as things go on, because you'll be implementing something like this for your first homework as well. But the point I want to mention is good features are important. Good features very often end up being the difference between a good learning-based solution and something that doesn't work. And it's very easy to come up with bad features. For the names, for the badges, I came up with one really bad feature here. Is there a day of the week that begins with the last letter of the first name? I mean, why? On one hand, that might be the true function that I have in my mind, but potentially, this is completely unlearnable. Yes.
Well, it's not a bad feature if that's the function, right?
It's not a bad feature if that's the function, exactly. But I can keep coming up with, is there a day of the week that begins with the last letter and something else? I can keep making it more and more complex. At that point, you're just probably fitting the noise. Remember that finding a good feature is not the same as learning, because in some sense what we try to do is come up with an over-complete set of features and then let the learning algorithm figure out what's the best ones.
So with that bad feature that you have, if you had encoded the last letter of the first name as one of your features, just the letter
Sure.
like you did before, it seems like your learning algorithm should be able to determine that certain letters are, so this might be a redundant feature.
It's possible, it might be a redundant feature, but you can easily come up with bad features that are not redundant. An example of a really bad feature is when I read the name, I toss a coin. And if it's heads, then the feature's value is plus, otherwise the feature value is minus. Now you're trying to learn to randomness. Clearly that's not going to work. That's an example of, that's certainly an example of a bad feature. What we'll not see a lot of are how to design features. That's something that you learn by doing really, and by being a domain expert. And if you want to design a classifier that decides whether a bridge is going to collapse or not, you better know about bridges. So that's an important point and often forgotten, but it typically comes with experience, and hopefully you'll pick it up as we go along. So all we have done so far is a big soliloquy on instances. The next thing here is labels. What are labels? Just to remind you, we want to find a function that takes an instance and produces a label. And let's focus a bit just on the labels. And there's not much to say really. The label space on one hand is probably one of the most important things that decides what kind of learning algorithm you use, and it also separates the kinds of learning algorithms or based problems. Just based on the label space, you have different names. So we saw an example of classification, and classification is the case where the outputs are categorical. You can have binary classification where there are two categories, plus minus, true, false, spam, not spam, 0, 1. You can have multi-class classification where you have k possible labels, and we'll see a little bit of multi-class later on. We'll spend a lot of time on binary. There's structured classification where the output is actually a graph. It's a discrete object and it's a graph. And it comes with its own interesting sets of problems. And as for almost all this class, probably all this class, we'll be looking at classification. Sometimes the label can be numeric. It can be a number, and you can have regression where you want to find a numeric value, or you might be given a list of examples, a list of points, and you have to rank them. So here's a machine learning problem. I type a search query, and it goes to the Google servers, and Google just identifies all the web pages that contain my search query. There's a large list, probably thousands. And now there's a classifier that has to take this list of 1,000 problems and rank them somehow so that the most relevant one shows up on top. So ranking can be seen as a classification problem. Or another example is a much lower complexity ranking example is where you want to produce a star rating on Yelp. You have 1 through 5 stars, and a 5-star is closer to a 4-star than a 1-star. And that's where the encoding can actually reflect that. You can use 1, 2, 3, 4, 5, and you don't have to do this binary encoding of these numbers. There's not much else to say about labels, honestly, other than the fact that they exist and they pretty much define the problem, and the fact that we'll be looking mostly at classification. One of the most important things that, at least probably the most important lesson for today, is about hypothesis spaces. And remember that the goal of learning is to find a target function, and you have to search over the space of functions. So what we need to do is define the space that we search on. This set of functions is called the hypothesis space. And defining the hypothesis space is crucial. It almost makes or breaks learning. And I'm going to give an example that at least some of you have seen before. If you've seen this example before, let's leave the fun for others. I'm going to argue that machine learning is impossible. It's just a meaningless and pointless endeavor because I'm going to prove to you that machine learning doesn't work. So, say we have, and I'm going to prove it by example and curious hand waving. Consider this function which takes 4 booleans as inputs and produces 1 boolean as an output. So it's a boolean function. And say I give you 4 or 8 or 7 examples of this function. The target function is hidden from you, and I give you 7 training examples. So the question to you is, what is this function?
If x4 is true, then it's true unless x2 is true.
So can you say that again?
Y is true if x4 is true unless x2 is true.
So it's x4 and not x2. Is that what you're saying?
Yeah.
Yep.
So does this fit all the data?
Yes.
Are you sure this is the function?
Let's expand out the table.
I can't see who's speaking, so okay.
Can we look to see any more of the data and see if the function is correct?
This is your training set.
Not enough data. It's a function.
It's a function that fits the data.
Right.
In fact, the thing is, there are many functions that fit this data. You have 4 bits, which means there are 16 rows in this truth table. I have only shown you 7, but you can think of this last column here, this column, as a 16-dimensional bit vector, 16 booleans, and every assignment to that bit vector is a different function. So there are 2 power 16 boolean functions. In general, if you have n dimensional booleans, you can have 2 power those many functions. That's a lot of functions. And first of all, do you see that there are those many functions? Okay. And what I've done is I've given you 7 of these rows, and I'm asking you to fill up the rest of this table. Right? But how could you possibly know this? Without seeing every label, every function that you invent, I'll give you one more example that contradicts it. I can keep doing that till you force me to reveal the entire table. So for example, let's say I show you 16 rows, and you find a function that fits all these 15, let's say I show you 15 rows, and you find a function that fits all these 15 rows, and I hide the last one. You give me a function, I apply the function to the last row, and reverse the bit and say, haha, you got it wrong. If the teacher is adversarial, students learn nothing. And that's a general life lesson too. So, how could learning possibly work? In the worst case, learning is impossible. Do you see this though? Any questions about this? And this is just for Booleans, where you have finite spaces. Once you move to real dimensional spaces, maybe things are going to get worse. And this is also the case where there is no noise. I can be adversarial by even adding more noise as well. Yes?
Well, you could argue, well, maybe it's not exact, but it performs, by some metric, it performs good enough, or...
That's not a completely valid argument, because let's say I give you half this table and you produce a function, and I will label the other half of this table by the negation of that function. So your performance is going to be 0. In a truly adversarial setting, the performance of any learning algorithm will be 0. Yes?
It sounds to me like you're describing science, right? Things tend to fall. We're just, that's what we see.
Sure, but how do we formalize that intuition? So the question now is, at least, hopefully, some of you are feeling uncomfortable in a class that's supposed to teach you machine learning, and in the second lecture you hear that learning doesn't work. So I need to fill up the rest of the semester. So let's get some ideas. How could learning work? Yes?
Well, I think first of all you need to have a large enough sample space to collect data on, and then you need to have something that will take a good approximation, a function that will have a good approximation of the data. So it might not be 100%, but it will be close to.
But in the worst case, it's going to be 0%.
Yeah.
No matter how much data you have, unless you've seen every data point. Yes?
Should be like some way of just like ruling out a bunch of, like shaving a bunch of space off of your like result space. You have like a situation, and then you just have to like disregard, like say like this, all this stuff is extremely unlikely, so we're just not gonna consider it.
When you say stuff, what do you mean?
Like outcomes, like if you, like for instance, like if you like walk into a room, there's a person in there, and they like say hello, like you could come up with like infinite reasons why they said hello to you, right? But in the context of the situation, you can probably narrow it down to.
I like the direction. I like the thought process. Can someone else take that and run with it? one more person and then I'll move ahead. Yes?
Maybe it's about the frequency of the data, like same kind of data is coming 80% of the time, so we'll take this 80% of time and one or two instances are not working, so.
That's kind of an orthogonal point, which is also very good, but I'm going to follow up on that one because your point is probably more relevant to about lectures in maybe mid-September or probably early October. Two hands. I saw yours first.
I think formalizing what he said as domain specific.
Okay, that's one point. I think between many of you the answer is there. One more and we'll move ahead.
Okay, I was just thinking that the worst case scenario might not always be the scenario, right? It is the worst case scenario. In that case, learning might be 0, but for a regular thing.
Right, so you're hoping that life is not adversarial and you move on. And in fact, that's pretty much it.
Yeah.
The solution is to restrict the search space. If you're searching over a set of all functions and somehow you believe that, no, not all functions are possible. There are 2 power n functions, but only a small subset of them are ever going to happen. So let me just search among those. Remember that the hypothesis space is the set of all functions that we believe are possible. And what I didn't tell you here, when I showed you this slide, is I never said that the search space is all Boolean functions. You all automatically assume. I just said this, or maybe I said it's all Boolean functions. You should check the video. But what I meant was, we only care about functions that take these 4 bits into 1 bit. Doesn't have to be all 2 power 16. Maybe a subset. Maybe a very small subset. And some of you came up with this example, x4 and not x2. And you implicitly disregarded really complex functions that might have also fit this data. So, at least for today and for a large part of the semester, probably the most important lesson is learning is impossible if you do not restrict the hypothesis space. Instead of looking at all Boolean functions, we look at well-behaved subsets that we believe, as a domain expert, are possible. And I've just listed some examples of Boolean functions that are well-behaved. And when I say well-behaved, I mean the number of such functions is small. So I could do just simple conjunctions or monotone conjunctions. If you have 4 bits, 4 inputs, x1, x2, x3, x4, and I can take any subset of them and put a conjunction, but without negation. There are only 16 such functions. I could do say a simple division. Yes?
Would you say that badge problem is a well-suited use of...
Can you speak up a bit?
Would you say that the badge problem is a well-suited problem for machine learning?
A what problem?
The badge problem.
The badges?
Yeah.
Yeah, probably.
This could be any arbitrary function.
It could be, but there was a human who created that function.
But it could be the days of the week, exactly. So
yeah, and you're just hoping that that function was not created in an adversarial fashion. That's pretty much it. And think about it this way. I mean, from a practical point of view, this question would not have existed in a machine learning conference if it was not solvable. That's kind of neither here nor there, but potentially, yeah, sure. I could have tossed a coin and produced a label, and you'll never find it. Did I see another hand?
Question?
Yes.
Suppose that that was in fact what he did, that he tossed a coin every time. Is there a way that you could detect that? Or are you totally hopeless?
It's hard to detect that. Maybe, maybe not. At least not using anything that you'll see in this lecture. Okay, so there are many simple functions that we can use. And I'm going to show you an example of one such function, which simple conjunctions or monotone conjunctions, which are all functions of the form xi, xj, and xk, or something like that. So, for example, if you have a conjunction that says x1 and x2, this will take, say, 1, 1, 0, 0 to 1. This will take 0, so on. This is a simple conjunction. And what is not an example of a conjunction that's not simple is something that has a negation, not x1 and x2, because of this negation here. And now the question is, okay, I've restricted the search space. Can I find a function that's consistent with this entire data set? The good thing about having 4 inputs and only 16 functions is you can define a learning algorithm which is the following. I need to search over functions. Let me list every one of them and see if it works. And that's what I did. So for example, there's one conjunction which ignores the input and always predicts false. And this has this counterexample, this example that's this one. So if you always predict false, the label for this example does not match that function. Another case could be if I predict x1 and x2, then the counterexample is this row. x1 and x2 are both true. The training data says the output there is 0, but this function would say that the output is 1. So I can list all possible and I can list more. There are 16 functions and I listed all of them. It turns out for every one of these 16 functions there's one counterexample in the training data. So what has happened here is that we have reduced the search space to such a small set that there's not even one function in the search space that fits the training set. Our hypothesis space is too small, which means that we've kind of lost the game here. On one hand, we want a small hypothesis space because otherwise we're never going to get to the end of this. On the other hand, we've managed to lock ourselves into such a small hypothesis space that nothing works. So that's the risk we run if we minimize the search space. But who said the only possible way to reduce it? Another, and we'll see that in a minute. But the question is, how do you even get to decide which subset of functions is valid? And the answer there is, you just stare at the data a bit and you use what you know and pull out a space from thin air. Okay, but then what if I do that and turns out that nothing works, like what happened just now? We had a hypothesis space that's just 16 functions, nothing works. What happens? Well, basically we're back to the drawing board, and that's the tension here. On one hand, we have to find a hypothesis space that's small enough that we can actually learn. On the other hand, we have to find a hypothesis space that's large enough that it, with high probability, will contain a function that we care about, that fits, that's at least consistent with the data. Questions about this?
I'm having trouble understanding how you said you pick the hypothesis space just by looking.
We just try to find a small enough hypothesis space that works.
But is it like, are you doing it manually?
Can you speak up, sorry?
Is it manual research? Is it based on what knowledge you have?
Yes, it's based on domain knowledge. And the real answer here is actually something that I'm trying to avoid saying, which is you need to find a hypothesis space that is large enough that you don't have to think too hard. And we will actually end up using we'll spend a lot of time using one such hypothesis space, which is the set of linear classifiers. It contains a lot of these interesting functions. But just for illustration, another hypothesis space is a set of functions called M of n rules. And M of n rules are just a function that shows up. I've only seen this in class examples in machine learning classes, so I don't think this is really. Anyway, it's defined as the following class of functions. You have a lot of features, Boolean features. You pick n of them. You designate n of them as special. And the function is, if at least m of those things are true, then the output is true. So for example, I have designated x1, x3 and x4 as special. So in this case, n equals 3. And I want to say if at least two of them are true, if at least two of x1, x2 and x4 are true, x1, x3 and x4 are true, then the output is 1, otherwise the output is 0. Is that class of functions clear? Is that a well-defined class of functions? Is it a finite class of functions? Okay. And is this function that's written here consistent with the data?
Yes.
Are you sure? The third row. This one? This works. And this works. What about the falses? No what? The first one works.
They all work.
They all work. So maybe this is the true function. Maybe it's not. So then what I want you to try is when you go home, first of all, how big is this set of functions? Is this class of functions as big as the set of all Boolean functions? And this is a simple exercise in combinatorics. Just counting. Are the number of m of n functions 2 power 2 power n, or is it a very small subset? Can I put them on a slide? Maybe I can. And how many of those functions are consistent? So one of the things that is kind of still bothersome is, sure, I found a function that fits the data, but how do you know you're right? You don't. You don't. You just hope you're right and prove a theorem that says that eventually we'll get to that. We prove theorems of the form with high probability. If you're right many times, you will be right in the future, provided you pick a function, you pick a hypothesis space that's small enough. And these kinds of statements are what constitute learning theory. So there are two competing. So before I go get into this, are there any questions about this? Yes.
What if we have two functions which qualify all the inputs?
Then you need to have some sort of prior knowledge or prior way to rank functions. You need to say that if there are many functions that agree with all the data, then which one do I pick? Your learning algorithm should incorporate a mechanism for choosing functions, not just based on the data, but based on some prior belief. And most algorithms that are under the umbrella of modern machine learning have that property.
So we can use active learning or the other one which was where we take the environment learning from the user?
I don't see how that connects.
So it's like, suppose I'm not sure about which two functions are correct, maybe I can go to the user.
Yeah, you can potentially go to the user or the teacher and ask, is this the right one? Yeah, sure, that's another way.
Wouldn't that really usually not come up, since usually your data is going to have noise in it, so one function is generally going to be slightly better than another one?
Very often, but there will be many functions which are equally bad, and that's the best you have because of the noise. So you still need a way of ranking functions. And these are all things that will come up through the semester. I mean, today this is almost just a technical preview of the semester with one introduction of a new concept, which is the hypothesis space. But, okay. So, given what I have said, there are two sort of ways of thinking about learning. One is, given a finite training set, and only a finite training set, learning is a mechanism that removes remaining uncertainty or tries to reduce remaining uncertainty. If you know that, for example, a function was a conjunction, then all you have to do is find a conjunction that fits the data. So before the training set comes in, there was uncertainty. The set of all conjunctions were open, were fair game, and suddenly the data comes in and rules out many of them. And in the example that we saw, it ruled out all of them. Did I see a question here? Yes.
When you set a hypothesis space, right, you say a function matches whatever data you get. Do you still continue to look for other functions which match the data, or do you stop there?
Well, now you're asking an algorithmic question. It depends on what your algorithm is. It depends on how you design this process. Maybe you find you rank functions. You take all your data and think of it as this is a very bad learning algorithm, but you take all your data and then list out every function that exists and assign a numeric score to them. And then go over this list and take the top one. Turns out it's actually not too bad, but it turns out that we can do this more analytically and save us the trouble of listing every function. But your question was about whether if you fit all the data, then do you just stop there? Maybe not. Maybe there's noise in the data, maybe there is nothing that fits all the data, and so on.
Or maybe we are getting the similar data in the first set.
What does that mean?
It's like maybe I have 80% of data which is similar and 20% which is for the other function, and in my first set of data I have from that 20%. So maybe I will be selecting a function which is kind of not generalized version.
So you're talking about a validation set?
Not exactly.
Okay, we'll take that offline. But the main lesson for today really is learning requires guessing a good hypothesis space. Very often it's no better than a guess, and if you're going to make a guess, we need to be sure why we are guessing a good hypothesis space. And we'll be talking about a few hypothesis spaces through the semester, and sometimes it's possible that nothing that you guess, no function in your hypothesis space fits the data, and yet you want to find one that best fits the data, one that makes the fewest number of mistakes. Maybe nothing is consistent with every example, but then you can start asking about least inconsistent. Okay, so that covers three things. We talked about what's the instance space, what's the label space, and what's the hypothesis space. The next question is about what learning algorithm do we use. And that's really a question for the rest of the semester, because I don't think I have enough time to talk about all learning algorithms today. And question of how do you evaluate? Yes?
Is it usually possible to use some kind of learning algorithm to define the instance space and the label space and the hypothesis space? Or is it something that we have to explicitly think about and program into our applications?
Very often you end up having to program this. Learning features, for example, is actually a very hot area of research in itself. You can think of features as representations. How do you represent input? And learning representations is really an unsolved problem. Learning hypothesis spaces is actually even harder, because now you're making the problem more difficult computationally. And so what you try to do is instead decide a broad class of hypothesis, a class that's broad enough, and then impose these conditions that rule out things very easily, or impose conditions that rank the more complex functions penalize the more complex functions. Did someone? Okay, so that's that. Now, given that there's still 10 minutes left, I'm going to just give you a preview of the next lecture. or in fact actually it's just a continuation of this one. So in some sense the main point that we want to do is pick a big enough hypothesis space that's still small enough, and we want a hypothesis space that might contain the true target function. And another word that I use for the target function is concept, the true concept. The concept is just another name for target function. Sometimes you'll see the word oracle thrown in. It's just a function that we don't have access to. And you might have seen some of these hypothesis spaces before, or at least heard of them. We have the space of linear classifiers. If you've heard of perceptron or support vector machines or logistic regression, they're all linear functions. Decision trees, some of you might have seen decision trees if you've ever taken an AI class or something. That's another class of hypothesis space. If you've heard of multi-layer neural networks, that's a more complex class of functions. Grammars one way of thinking of a grammar is it's a hypothesis space. And one sort of a naive version of learning is you find a function that fits the hypothesis in your hypothesis space that fits or best fits the training data and hope it works. You just hope it generalizes to new examples. So this gives us the main issues that we have to run into. The first one is the modeling problem. The modeling problem is is your problem a machine learning problem at all? Someone asked, is the badges game a machine learning problem? I don't know, maybe I could have just written a program. So the first question is, how do you take your problem that you care about, maybe you want to build a car that can drive itself, and formulate it as a series of decisions or maybe as a complex machine learning problem, or maybe a simple one. How do you represent examples? How do you represent data? How do you represent instances? What are the features? And what is the learning protocol that you're going to use? Are you going to use supervised learning? Most of the time we'll do that. Or are you going to use something that is more, that has less supervision or has more interactions? The key point here is a good representation. And representation is, there are two kinds of representation. One is the problem of representing examples as features. So that is this problem of identifying a good feature space. And a completely different representation problem is, I want to find a function, a space that can possibly represent my concept. So that is the selection of hypothesis space. And then from the algorithmic point of view, there are many, many questions. One is, well, first of all, what is learning? How do you know that one learning algorithm is better than another? And that's the question that will bother us for pretty much the rest of the semester. And what is overfitting? Or what is success actually? How do you know whether your function works or not? And if you believe that learning is generalization, then how do you measure generalization? How do you measure generalization programmatically? How do you measure formally, mathematically? How do you define it? And of course, because we are in the computer science building, we have to think about how long this will take. If I give you a learning algorithm that's perfect, will truly find the correct answer, but will take 100 years. And this classifier is something that will predict whether you have a cat in a picture or not. Maybe most of us will say, I don't want it. So we need to quantify the computational complexity of learning. And just to give you a hint of how we might do that, think about learning as search. If we have to search over 2 power n elements, the search is going to take long. If you're only going to search over a small number of examples, search is going to take a small number of target function hypotheses, then the search will take much less time. So the size of the hypothesis space not only has to do with whether you believe you can learn, but also it has to do with how much time it will take. Okay, I'm going to stop now unless there are questions. And in the next lecture, we are going to continue with this general thought, and we'll see our first learning algorithm. We'll look at decision trees, and we'll step through how we can learn decision trees. And just as a final reminder, please get done with the quiz. I think it will be available for till September 3rd. And those of you who still need permission codes, please email me.